You know, when we think of plastic, we usually picture something totally static, right? Like a water bottle or a phone case, it stays exactly the same until it inevitably breaks or gets melted down. But, actually, scratch that. What if that wasn't the whole story? Imagine if a material that looked and felt exactly like standard plastic actually held a physical, structural memory of its original form. Well, welcome to this explainer. Today we're unpacking the totally mind-bending science behind shape memory polymers and 4D printing. These are smart materials that are just absolutely redefining the boundaries of modern engineering.
So let's just jump right in and picture this scenario. You've got a solid, highly detailed 3D printed object. Now you heat it up just a little bit and then completely crush it into some unrecognizable shape. You freeze it right there. To anyone else, it literally just looks like a crumpled up piece of junk plastic. But then, and here's the crazy part, you magically restore it to its perfect original geometry just by adding a gentle bit of heat. I mean, it sounds exactly like science fiction, right? Or maybe some kind of magic trick, but it is a highly documented, totally engineered reality.
What we're really looking at here is the shape memory cycle in action. Think of a permanent form, maybe something like a perfectly folded paper airplane. Through a mix of heat and physical force, it gets compressed or folded completely flat into a new, temporary shape. And it'll actually stay that way indefinitely, just waiting. That is, until the recovery process is triggered by reheating it, which causes it to autonomously unfold and recover those original wings.
To prove just how incredibly dynamic this stuff is, Dr. Kim orchestrated this absolutely cinematic ship-in-a-bottle demonstration. So picture this. They 3D printed an intricate infinity ring that was mathematically way too large to ever fit through the neck of a standard glass bottle. Then, they heated this ring in a water bath to 80 degrees Celsius, heavily compressed it into a tight little bundle, and cooled it at room temperature to freeze that new tiny shape. They easily dropped this compact disguise right into the bottle. And then, the grand finale. They just added hot water. Inside the glass, the polymer literally woke up, expanded back into its permanent infinity ring shape, and became permanently trapped inside. No way out.
And the best part is, this isn't just some theoretical lab model. Those vibrant orange structures, including that exact infinity ring we just talked about, are entirely real. By using digital light processing, scientists have been able to print insanely complex 3D geometries. We're talking everything from double platforms to really dense cubic grids, all utilizing that exact same shape-shifting ink. So what's the secret behind this magic trick? It's called the shape memory effect, or SME. For these polymers to actually pull this off, they rely on two distinct phases. First up, you have to have a programming phase where that temporary shape is locked or fixed into place. Then, secondly, there has to be an environmental trigger. Usually that's a specific temperature. And that initiates the recovery of the permanent shape. Without both halves of that equation, well, the material just behaves like your everyday, boring plastic. This whole thing translates into a really strict, four-step thermomechanical procedure that basically lets us manipulate these plastics totally on demand. Step 1. You heat the material above its transition temperature so it gets nice and pliable. Step 2. You apply physical stress to deform it into literally whatever temporary shape you want. Step 3. You cool it down while holding on to that physical stress, which essentially locks or fixes the shape. And finally, Step 4. Whenever you're ready, you just reheat it without applying any stress, and boom, the material naturally snaps right back to its permanent form.
Now, to truly grasp how this works on a microscopic level, we kind of need to shift our perspective. Try not to think of the plastic as a solid block. Instead, imagine the polymer's internal molecular chains as thousands of tiny, highly tensioned springs all tangled up together. At room temperature, these springs are locked into a rigid, totally random arrangement. But the second we add heat, we're basically giving those springs the energy they desperately need to stretch, move around, and untangle.
When we actually map out what's happening to those molecular springs, we see that heat pushes the material past what's known as its glass transition temperature, or TG. Basically, this is the threshold where the material shifts from a rigid, glassy state into a highly active, flexible, rubbery state. While it's rubbery, you can stretch those springs and orient them. Then, when you cool it down, the springs get frozen in that stretched-out state, storing up all this elastic potential energy. Reheating it past the TG releases that stored energy, causing the springs to violently uncoil and snap the material back to its original shape.
Okay, so here is what makes the latest research so absolutely groundbreaking. It's the scale at which all of this is happening. Scientists have formulated a single commercially accessible shape memory ink that works across completely different extremes of size. For the macro scale, they use digital light processing, or DLP, with UV LEDs to print objects you can easily hold in your hand. But using that exact same core chemical formulation, they can switch over to direct laser writing, or DLW. That uses a tightly focused femtosecond pulsed laser to print structures at the absolute micro scale. We're talking structures so small they are measured in sub-micrometers. That's a real game changer.
At this microscopic level, things get truly wild. Researchers have orchestrated this mind-blowing display of microengineering by printing tiny, smart box-like structures. Because they're 4D printed, meaning they actively change over the fourth dimension, time, these microscopic boxes can literally be programmed to open and close when exposed to heat. They successfully used these thermal actuators to physically trap and release tiny microspheres. They basically created microscopic robotic claws out of smart plastic.
And you know, this system doesn't just look cool under a microscope. The math behind it is staggering. In macroscopic tests, these polymers boast a 98% shape fixity ratio. To put that into perspective, it means that when you program a temporary shape and freeze it, the material holds that disguise almost perfectly, with only a tiny 2% deviation. On top of that, it has a 97% recovery ratio, meaning it springs back almost flawlessly to its permanent design. That level of extreme precision is exactly what engineers need to take this tech out of the lab and into the real world.
Grounding all this science in real-world applications, Make Magazine actually highlighted a brilliant demonstration out of MIT by researcher Vikas Srivastava. He showed that these exact shape memory polymers can be chemically tuned so their glass transition temperature, that all-important trigger point, is perfectly matched to human body temperature. So you don't even need a hot water bath or a heat gun. Literally, just the natural ambient heat of the human body is enough to wake the polymer up and trigger its transformation.
Because these materials can be activated by something as gentle as body heat, they are revolutionizing so many different industries right now. In biomedicine, imagine a highly compressed stent being inserted through a tiny incision, only for it to gently expand into its perfect permanent shape once it's safely inside a warm human artery. Or over in aerospace, engineers are designing satellite components that can be tightly folded up for a rocket launch and then autonomously self-deploy out in space using just the heat of the sun. We're even seeing this applied in soft robotics to mimic natural human muscles, and in smart textiles that can actively adjust their own fit or breathability. So this single breakthrough is rapidly creating this vast, interconnected ecosystem of new applications. Whether the material is triggered by light radiation, magnetism, electricity, or just water, the core concept of a programmable, shape-shifting material is finding a massive home in flexible electronics, cutting-edge surgical tools, and autonomous robotics. The bridge between raw chemical theory and everyday practical technology is closing fast for sure.
So I'll leave you with this final thought. We are really standing at the edge of a whole new era in manufacturing. As our engineered world transitions away from static, lifeless plastics and moves toward active, remembering materials that can adapt and heal on demand, what impossible magic trick will science make a reality next? Thanks for joining me on this explainer, and definitely keep your eyes open because the future is literally taking shape right around us.